Okay, can everybody hear me? Yes, yes. All right, so last time, let me see. Okay, well, everything is fine. Last time we said we are going to continue on this problem, and I just wanted to remind you, because similar these types are the problems that we are going to solve for next week, and then as we prepare for the final, one of the problems in the final will be from this material, like what we are going to solve, the problems we are going to solve today and the next week. And another problem will be from the first part of the class, all right? Now, some things that terminology that we want to establish as we talk about design problems using transmission lines. First of all, as we've mentioned in the past, transmission lines are distributed elements. It says here on the side. So you can see that. I would upload these after whatever we add to this lecture. And then I would like you to cover it, to go through this for Monday. And also I will put the videos, because especially for Smith charts, it's very useful to not just see what I have done, but also to see the progression of doing this, and then you can follow me doing those things from the video. So it's useful. Not so much video useful for, the video is not as much useful for other things, but specifically for the Smith chart is. Okay, transmission lines, we call them distributed elements because they have a physical size, all right? It's a physical length, rather. As opposed to R, L, and C, which are the traditional resistor, inductor, and capacitor, which we call lumped elements, because they do not have a physical size, at least anything that we need to consider. Yes, they are real things. Of course, everything real that we make has size, but their size is so small that we assume that it does not exist. So we call them lumped elements. A design, as it says here, that has both distributed and lumped elements is called hybrid design. All right, because it's a hybrid between distributed and lumped. And a design that has only distributed elements is called monolithic. Can we use the name monolithic for a design that has all lumped elements? No, because lumped elements by definition, even if you put them on a board, I don't know what kind of boards you had for your circuits class, where you would add resistors, inductors, and capacitors in different spaces. But in between, they're connected with some lines, all right? So everything other than monolithic is hybrid. And there's nothing else. And hybrid is something that includes both distributed and lumped. Monolithic is what includes only distributed elements, all right? Okay, in this particular problem, so a designer, for example, will have to take those issues into consideration when they develop the architecture. For me, for us, for this class, I will always give you guidance on how to think about the design, all right? I'm not gonna give you all three of them. If I give you a problem, and the problem says that I have a source, you know, that looks like that with whatever amplitude, whatever frequency, I give you whatever internal impedance is going to be real, all right, for us to simplify things. And whatever load I'm going to have at the end for you, I will give you guidance on what kind of design to make. All right, I'm not going to ask, I'm not going to give it undefined so you wonder whether you can do this, the hybrid or the monolithic. All right, so I will tell you I wanted to use only transmission line elements. All right, only distributed elements. Or I will tell you you are free or I want you to do a hybrid design. I will be very specific, but here we are going to do both. And that's how we started last time. I'm not going to cover the whole thing because I want to proceed. So where we stopped last time was on this Smith chart. And now that, of course, is a monolithic design, all right? Everything is distributed here. And now I will need to remind you what the various things mean on the Smith chart. So to do that, I will go to this transmission, this figure here. We have, well, not really this, that's part of the design. This one, the first one. This is our figure, all right? Somebody gives us a load, they give us a source, and then they tell us to use the transmission line plus a stub. That's the last one we were working on. And the stub is nothing else but a section of a transmission line that is either what? Open or short. Here in the problem, they do not specify the third question. Let me see. The third question does not specify what kind of stub you want. It does not tell you use an open circuited stub or a short circuit. All right. So we'll see from the design which one you're going to choose. Okay. So now let's use this generic figure that we have written multiple times. We know that we have to use a transmission line, and we know that somewhere in the transmission line we have to add a stub. And what we said last time about stubs, and I'm going to that. All right, there are two types of stubs. Two types that have two different possible terminations. One is a series stub, all right, because we put it like this. So practically you add the stub along the line. And the other is a shunt stub. And the stub and your transmission line share the same ground, as we say, all right? So if your stub and your transmission line share the same ground, as it is here, this is called a parallel or shunt stub that you may see. Shunt. Or, okay. In this case, the transmission line has this ground and this one, and this here has its own ground. All right, so now how you make them, that's a different story. It depends a lot on what kind of geometries. I'll show you some examples. But so we have one series possibility of a series stub, the possibility of a parallel stub, and then the series stub can be either open circuited or short circuited. And the parallel or shunt stub can be either short circuited or open circuited. So practically there are four possible combinations. There are four possible stubs that somebody could use. Practical considerations, as it happens in every design, will tell you which one is the best solution, all right? Okay, so now, what we know in this is now our design. We know that for this distributed, where we cannot use a lumped element of any sort, we will have to go to the Smith chart, right? You cannot solve this problem with distributed only elements and solve it using the equations. It's going to be very complex. So the Smith chart is there for that reason. And what we know is the following. We know that we have our load and our source. We have a transmission line and a stub. And we then for that, whenever you go to distributed approach, and you don't use a quarter wavelength transformer, where the characteristic impedance, you don't select it, but it comes out of the design, you will have to select a characteristic impedance. And what did we say about what we select as a characteristic impedance? The standard is to go with 50 ohms. All right. Now, if in the problem that I will give you, I will also specify that. so you don't forget. But the standard, if nobody tells you, is to use 50 ohms. So we know that we are going to use a 50 ohm line. We don't know how long it's going to be, so that's an unknown. We know that we have to add a stub somewhere. We don't know which of the two, parallel, shunt, or series, we're going to select. And then we also know that in this stub, we are going to need to find its length and then decide whether it's going to be open or short. All right, so these are the things that we have to do in this particular case. All right, first thing you do before you go to the Smith chart is what? You have to normalize every impedance, you know, with regards to your characteristic impedance. You cannot use a Smith chart unless you normalize. Let me see here. So when I normalize my load, which is the antenna, the normalized value is 2 plus j.6. First thing you have to do is to start with your load, all right? And then you have to find it on the Smith chart. The Smith chart is a space where you can find a point for every impedance you can imagine. Any real value, any reactive, all right? Any capacitive in terms of any inductive. And all of this is happening within this space. And how do you accommodate zero values and infinite values? By these two ends. Here is 0 for resistances on the left side. On the right side is infinite. All right, we measure resistances along the horizontal line axis. Then we are looking at the innermost circle. All right, and I will show you is this one. So that if you go around, that's the innermost circle. And as a matter of fact, if I wanted to show it for you. Okay, let's see how we're going to manage it. It's not exactly, okay, it's accurate enough. In fact, for some of you who said how to do the circles, I advise you to use PowerPoint. Put your Smith chart. It's not going to be perfect. However, I have to tell you that it's going to be close enough to find good values. All right, you don't need to use a compass. All right, so that's how I did mine. And if you're very picky, I forget. That's it. The best for now. I'm going to spend more time. So this is the circle here where you see the values. This is the one. The upper half gives us positive reactive values, all inductances. For lower half, all capacitances. And this is when we use this to project, all right, their impedances, complex impedances. I make a note here because if you want to project an admittance, you have to do something different. And we are going to talk about this on Monday. So for now, for every impedance, you project all the resistances on this horizontal axis. You read them. All reactive parts here on this circle. Okay, upper circle positive, lower negative, inductive up, capacitive down. All right, so now I will remove, if I can, okay. So we don't do anything unless you absolutely need it, because it can get really congested. So now, first of all, what I do, I put my point my load, which is right here. Let me, right here. All right. And I say BB prime because that shows the load ZA, which is connected on my line at the port, the output port, which is BB prime. And how I make it, I find the circle, the red one that goes through 2, which is right here. And I write the whole circle. That all of the points of this red circle have the same normalized resistive component. All of the points of this red have a 2 for the real part. Okay, but each one of them has a different reactive part, imaginary, from infinity to 0. So how am I going to find my own point? I'm going to go around here with all of these values on the circle that I just erased and read from 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. That's where I stop, 0.6. And I draw the circle that goes through this 0.6 here, the green dot, and then until it terminates right here. I mean, the circle is huge. It goes out of the Smith chart, but this is the section of the circle that I need. And therefore, I write it here. And the intersection between the red and the green dotted circle is my point at BB prime, and this is my normalized impedance. All right, so that is where I start. Now, I need, where do I need to go from there? You remember what I said last time? What is the point of the Smith chart where I have a perfect match?
Right in the center.
Yes. Yes, the center of the Smith chart is where I have a perfect match. Now, why do I gonna go there? Because if I manage to add something like this, and at this point between D and C, if you like, let me see if I go. Yes, this is where I am. If I manage, let's assume that the point I'm gonna go at the center of the chart is the C prime. I know I'm gonna have to do more than just traveling on the line because I have to add a stub somewhere, all right? But if I achieve at this point, C prime, where I do not know where it, which I don't know where it is, if I can make this Z input at EE prime, at CC prime, all right? Not at EE, at CC prime eventually. If I make that input, the total input to be 50 ohms, then practically I will be done with the matching, all right? I wanna make the input impedance after I do everything somewhere around the point CC prime. I want to make it equal to 50 ohms. And if I make here my input impedance equal to 50 ohms, then everywhere else on the rest of the line, the matching is going to be perfect. Because if my input impedance at some point here, this is all qualitative, right? My input impedance somewhere here, eventually, becomes 50 ohms, the reflection coefficient there is going to be 0. And if the magnitude of the reflection coefficient is 0 at any point on the line, then it's 0 everywhere until I go to the source. So that's what I want to do. I want to find a point where I get to the center of the chart and I'm done with that. Okay, so that's how we are thinking. Now, my antenna impedance is not at the center of the chart, it's at BB prime. So, and I want to go to C prime. But I cannot go straight. I mean, I draw these green lines, but they're not lines I can travel on. All right? You remember we said you can only travel on the Smith chart on circles. There are no straight lines to draw. The straight lines will have the money to measure some things. Only circles. So And from BB prime, if I were to travel on this circle, if you travel on a circle that has the same resistance, that means that you change your reactance, all right? If you travel on a circle that has the same reactance, that means that you change your resistance. Then if you travel on the constant VSWR circle, what do? You just travel along a transmission line. All right, that's what you do. These three circles are extremely important to remember. So the purple one, which I say here, constant VSWR, is the circle that shows you that you travel on a transmission line. And you can travel forever on the transmission line. The more circles you make, the longer you go. If I go from BB prime over half a wavelength, I'm coming back to the BB prime. You remember we said that every half wavelength, your impedance is repeat. So if my load at BB prime is this, if I travel on this transmission line by half a wavelength, I'm going to have the same input impedance there. That's what it says. So obviously, if I keep traveling around that, I'm not going to do anything. I'm going to find where I will go as a stop, as an intermediate stop, like you go from one plane to another. You're going to go to New York, you have to stop maybe in Chicago or something like that. Really, this is what it is. And then change the route if there is no direct route. There's no direct route here for BB prime. So you go up, and then as you normally do with airlines, you have to find an intermediate stop that is not going to take you out of the way. If I want to go to Chicago, you tell me to go to New York first, I'm not going to take that. There are lines. In fact, if you try to get an air ticket nowadays, they will tell you crazy, they will take you crazy places. But it's going to take you 10 hours to go from here to Chicago. I'm taking many times, making flights to go to Greece. You cannot believe where they take you to go to Greece. I can go around the globe to go there if you don't pay attention. So that happens. But of course, here we wanna make the distance the shortest. All right. So I'm moving around, and then I'm thinking, where do I really want to go? Okay, I have to stop somewhere, but how am I going to select that stop? I'm going to select it so at the place where I stop, my real part has already become 50 ohms. See? That's how it is. I'm not going to stop anywhere. I'm going to stop exactly where my real part of the impedance, the input impedance at that point is 50 ohms, which means when I normalize it, the real part of the input impedance normalized is going to be 1. And there is only one circle that has a normalized real impedance of 1, and it's the one who goes through the center of the chart. All right, so I always want to stop there. That's going to give me the shortest travel, all right, to the center. All right, so then I stop, you see? And then I ask myself, where can I go? What kind of transportation I'm going to take to go to the center of the chart? And of course, I'm going to move along the constant resistance circle that goes through the center of the chart, because I can move on constant resistance circles, remember? Now, when I move through constant resistance circles, what do? I keep my real part the same, but then what do I change? I change my reactive part, all right? That happens, you know, if you move along this red circle, everywhere your real part is going to be the same, but your reactive part is going to change. The same thing with this circle, the one that I've taken to go to the center. I have not drawn the whole circle because then it's going to get very busy. All right, so try if you can to avoid. Maybe you can do it in the beginning to see it, but then try to erase the parts that you don't want, because it's going to be very difficult to remember where you are. And then use the arrows, please, to remind you which direction you take. It's very easy if you take the opposite direction to make a mistake. All right, so from here I'm going there. Let's try now to write down and translate all of this into what it means on my transmission line. Let me go down a little further. Okay, it means that I can, first of all, E prime is my stop. Remember, it's not my destination, it's the stop. And that stop was where my PSWR circle intersected with a circle that has 50 ohm resistive part. That is the E prime, okay? And in fact, on the Smith chart, I have it there. Remember that this point here is my E prime. So I stop there. But then I'm not done. I have to do something to add a reactive component. But I have to add a reactive component so it gets me to the center of the chart. All right, remember those two things as I'm going here. So I am at E prime. In fact, so I don't, let me do the following to help a little bit here. First of all, take this. I will place this a little further. Let me show you. Let's put this one here. E prime. And then, even if this is very small, I mean, it's all conceptual, all right? Because in reality, this is not an extra length of line. In terms of lines, they are right there. But at E prime, let me do this C prime. Since I did that change, put C prime here. I want to make this equal to 1. And here, you know, those lines is just to help you see the ports. This is one port, this is another port, all right, on the transmission line. There is nothing connection, no connection in there. But the Z input right there is exactly what I've read from the Smith chart, which is 1 minus J.85. All right. So by moving from BB prime, where I had that ZA, to EE prime, I made my real part 1 normalized, and now I have this term that I want to eliminate, which means these are all added later, but I will for now erase them so we can do them together. Okay. Which means that I have moved by a distance D, then also try to make it here. I have moved by a distance D that makes my Z input 1 minus J.85, but I want to make that equal to 1. I want to add something between EE prime and CC prime to make my total impedance at CC prime equal to 1. And in fact, this is what you have at Z EE prime is 50 ohms plus a capacitive component, all right? Now, what do I want to do? What do I want to add here? What I want to add between EE prime and CC prime is a stub. You see it here? I want to add a stub, which now I show it as a square, just conceptually, that has an input impedance, which is going to cancel for me that part. If my load here is capacitive, I want a stub that is going to give me an inductive impedance. That is going to be equivalent to an inductor, an inductor, or it's going to give me inductance. I want an inductive stub, as we call it, which then is going to cancel this part. All right? And if I do this between EE prime and CC prime, practically then I have achieved a perfect match here at CC prime. Okay. Now, stubs. There are the following thing you have to remember. Let's look at, did you see how I placed the stub here? I placed it in series. Why is that? Because this is an impedance. And if I want to cancel its reactive part, I have to add something in series. I have to add another impedance in series. All right, because the Z total input at CC prime is going to be the sum of these two. So practically, the reason I've done this is because Z input at CC prime will be my Z input at EE prime plus Z stub. The fact that I want to do this implies that the stub has to be in series. You see that? Because I sum up the impedances. That's why I put it here in series. I was forced to put it in series because I'm working with impedances. All right, so even if there are parallel or shunt stubs, in this particular case, I have designed it for a series stub. Okay, so now the question is, I know it's a series stub. The question is, what am I going to use? Short circuit or open circuit? Now let's see how we are going to figure this out. First of all, we know how much is the stub. The stub has to be from this expression here, and it should not be normalized because it's, I put 50 ohms, all right? So let's, so we want to make this equal to 50 ohms, which is the center of the chart when I normalize. Therefore, the stub has to be an inductive load of this value, which if I normalize to 50 ohms, because I use 50 ohms as characteristic impedances, both for the transmission line and the stub, if I normalize, it becomes this. So now, how am I going to design for this stub? All right, that's the next step. Okay, the stub is a transmission line that gives only a reactance. All right, it's either short or open, and the stub gives us only a reactance. So in fact, here, well, I did not have it there, but I will just mention to you that the stub, do you remember an open and short circuited transmission lines that we've done? So for example, let me do this here. Add a page here. All right, just so to remind. So this is review. Let's assume that I have a transmission line. Please. Okay, this one. I have a transmission line. And the transmission line at the end is shorted. Make it a little thicker. And this one. All right, and it's shorted at the end. A short will show it like this. This has a characteristic impedance in out, has a length L. And we want to know how much is the input impedance here of this stub, which I will call this a base. All right, how are we going to find that? You remember from the input impedance, the general formulation of the input impedance on a transmission line. The input impedance on a transmission line is equal to that. That's the load plus J Z naught tangent of beta L Z naught plus J ZL tangent of beta L. Okay, for a short, how much is this a bell? Come on, how much is the load if it's shorted? 0. This is 0. Then how much is this a base? This a base becomes equal to J Z naught tangent of beta L. All right. Now, if tangent of beta L is positive, so if tangent of beta L is positive, and what does that mean? That beta L, that means that beta L, which is 2 pi L over lambda, is between 0 and pi over 2. All right? Which means that in this particular case, L over lambda in wavelength is between 0 and pi and a quarter, between 0 and a quarter of a wavelength. So let me, in fact, excuse me, do it better like this. L, it's a quarter of a wavelength. Therefore, if your length of the line is less than a quarter of a wavelength, then your tangent beta L of the stub is positive, and the stub is giving you what? Is giving you an inductance. Inductive. Is equivalent to an inductance. All right? Okay, so now, here I know that I need a short-circuited stub, okay? So here the stub has only inductive components. There is no resistance. So I have to be on this outer circle, which corresponds to 0 resistance. All right, 0 resistance. Okay, then I need to go from this point here that I measured to 0.85. I have to go, this is at that point on the Smith chart. This is this a base at this point. It's going to be J.85. Okay. And therefore, I know that I would, if I go on the stub and I am at the end of the stub, the termination, which is short, I will have to be here, and I will have to walk. All right. Until I find the point where my impedance is that. And that is going to give you the length of the stub. Because here is 0 length, I will have to go to this number, and if you read it, is 0.112 lambda. And that is going to give me the length of the stub. So when the length of the stub in this particular case is 0.112 lambda, then Z sub S is normalized J.85. And therefore, that takes me now to this solution, where it tells me that if that becomes, now I can write my solution here. If that becomes 0.0, excuse me, what did I say? 112 lambda, then the input impedance here that I see here, all right, that is going to be equal, which is this one, I call it Z sub S, all right? Z sub S is gonna be equal to what I told you, which is J.85. Okay, so here you see it down here. There. Okay, now what else do I need to know? I'm at EE prime, but where is really EE prime? EE prime is down here, so I have already moved by a distance D. Did I say D sub S should be the other one? Let me see. Yes. Okay. So let me shorten this a little bit. So it comes here. Okay. D. How much is D now? We have to find out. How do we find this? We go back to the Smith chart. Okay. When I move from here, BB prime, to this point, all right, I move from my load to E prime, I have to calculate the distance. So I draw one line here and I read the number, 0.222 lambda. Then I connect to my start point. So this is my beginning. I'm stopping here before I turn around. And then I read it and it's 0.345 lambda. And then I take the difference between these two. And that tells me how much I'm going here, which is going to give me practically D equals let me see, 7, 4, 5, 7, 0.077 lambda. Okay, so I'm moving on the transmission line by almost 1/10 of a wavelength. So now when I have everything, so I have moved on the transmission line. Let me put it on the initial problem. This is too long, I'm writing it, but it's for your benefit to see what we are doing. Let me see, excuse me, all right. So I have put a series stub, but with a short. Maybe I need to show it here for a second at the end. Okay, let me, in fact, after the stub, show the whole thing. I will do it here. Right. So let me, for a minute. All right, see here. I need to, instead of doing the whole thing, I'll borrow this figure here. Copy. And then go here and put it at the end. Paste. All right, so now what I've done, I put at the end a short. All right, so I chose because the short was the shortest distance and it would give me a positive reactive load that I needed. I found D sub S to be 0.112 lambda. I found here this distance to be 0.077 lambda. And then I have 50 ohm lines here. Z naught. And I have also Z naught here, everywhere. You see that? And Z naught is 50 ohms. So practically, I have solved the problem. So the question now for you is, I know this to be 0.7, almost 1/10 of a wavelength. I know this to be almost 1/10 of a wavelength. And then I cannot define the rest. The rest, I'm very flexible in defining the rest of the line, the length, because any point after D, I will have matched. I will have matched the whole thing to the source. So I can use as much length as I need. And who is going to tell you what length, how much length you need? Your real problem. So here I try to put something together for you. Let's assume that my load is an antenna, which I call a patch antenna, and it's made out of microstrip. It's in microstrip form. So there is a ground, all right, at the back. There is a load, and then somewhere here where you see A prime, I would connect my source. My source can be like a transmitter, all right, the whole subsystem. But it's right here. I have designed it so at this point, what I'm going to see is a source that has 1 volt, RF, AC rather, and has an internal impedance of 50 ohms, and then has a frequency that what we use to design it. How are you going to then, in this particular case, there are 2 constraints, all right? So now your layout is what we have solved the problem correctly. But now you're going to go and somebody's going to tell you, you know, I forgot to tell you that we're going to use microstrip to do it. And this is how much space you have, and it gives you enough space, all right, obviously, because they're not going to be disclosed. A tenth of a wavelength is already very small. For example, if you are at 10 gigahertz, your wavelength is 3 centimeters. How much is a tenth? 3 millimeters. This is way bigger than 3 millimeters. Consider that this here, the length of this, has to be half a wavelength to operate the antenna. So it gives you enough space, all right? Don't worry about that. The only problem in this particular case, it's a microstrip. So how am I going to put a stub in this that is in series? You cannot use a series stub in a microstrip, because always there is going to be a ground underneath. And whatever I do on the surface is going to have the same ground with my transmission line. Which means the only way of doing something here is in shunt configuration. All right? So now you realize that my original geometry, or how they're going to make it, whoever the system designer was, decided to go to microstrip. Now I have to go back and do my design more or less with the same kind of thinking, but instead of a series stub, I need to put a shunt. All right, so now you go to a redesign. That would be the case if your structure was like that. And let's assume, because I will give it to you as homework, I will give you this problem as homework, where you're going to have to design it with a shunt stub. But after you design it, what I'm going to have here is the following, how I'm going to make it. And that's a real design that people make, as a matter of fact. So I'm going to add a section of a line here, microstrip, and then a tenth of a wavelength, approximately. Then I will put my stub, a tenth of a wavelength, and then I will come here. And your stub is going to look like this. All right. And that is how you're going to match to the source an antenna with a transmission line where the section, the front part of the transmission line that's connected to your load is going to be 0.077 lambda, and the width, the length of this stub, which is now open circuited, because I cannot, I mean, I could do it short circuit too, but I have to open a hole, which is all kind of a problem, right? If I have to fabricate a hole. What if I give it like end, like this is going to be short, excuse me, open circuited. So you're going to see in the homework that I will give you a similar problem. I will give you the same values so you can, or very similar, so you can follow what I did for the class, but it's going to be on a microstrip. So now you're going to realize that your stub has to be in parallel, because the stub, which is this, is going to share the same ground with a microstrip line. Do you see that here? This is how real designs are taking place, all right? And you have designed a true matching network, which is real. I mean, if we had a lab for this class, you could make it, and then you could measure it, all right? But that's how exactly we did that. Any questions? Okay. If you have no questions, we are thinking right on time. I'm not going to give you a quiz. I wanted to tell you that next week on Friday, next Friday, and the following Monday, I'll be on travel for family reasons. I mean, good reasons. Not any problem. My granddaughter is baptized and I have to go because I missed the other one because of COVID. So I want to do that. However, I'm going to record my lectures and you're going to have available both the Friday and the Monday lecture. And there are going to be problems. We're going to solve these kinds of problems. All right. And I'm going to record them. Will be like in video, like normally we have with Zoom. I will put it, you will find it in your notes. I will also put the recordings of Monday and Wednesday and today. Also, you will see them in your modules, all right? Because I would like you, as you solve problems, to go back to the recordings to see how I did things on the Smith chart. It's better to take a little more time and see how I did things as opposed to just doing something wrong, all right? And as I do things, you can hear my voice, what I say, so you will be able to correct them, if anything. For Friday and Monday, you will do that. Tuesday is a redefined day. And we are going to have a class on Tuesday, but it's to solve problems. And those is going to help you for the final. All right, so, and when is the final for these classes? Is it on the 13th? Yeah, so, okay. And I will keep office hours next week for any questions you have. I mean, this coming week and the week after, until you have the final to ask many questions. All right, anything else? Any questions you may have? Anything that I missed? All right, thank you so much. Enjoy the weekend.